welcome back. In this video, we're going to use Rolle's theorem along with an old theorem from chapter 2 to do a proof. So let's first look at what Rolle's theorem says. So there's three hypotheses or assumptions in Rolle's theorem. So we're going to suppose that 1, f is a continuous function on a closed interval from a to b, and it's differentiable on the open interval from a to b. So what does this mean? This just means that f is defined at every number between the numbers a and b, and also it's defined at a and at b. And it's differentiable everywhere in between. So it might not be differentiable at A or at B, but it's at least differentiable everywhere in between. And then the third assumption is that f of A is equal to f of B. So those two numbers, A and B, have the same y value or y coordinate. Let's see what it looks like. So here's A and B. And if the function f has the same y value at a and b, and it's continuous in between a and b, and differentiable between a and b, that just means it's nice and smooth, doesn't have any sharp corners, and it's got to look like this. So there's 2 points where x equals a and another one where x equals b, where they have the same y coordinate. So this is a function that goes up and comes back down. It could be a function that goes down and comes back up. Basically, it means that when you have a function that's continuous and differentiable, it doesn't skip over any points, and it's nice and smooth, it has to have a turning around point, right? We can visualize that. It could be a local max or it could be a local min, but it's a turning around point. So the conclusion of the theorem is that somewhere in between the numbers a and b is another number c. So c is in the open interval from a to b. That's what it means to be in between a and b, where the derivative is 0. So f prime of c has to be 0. That just means it has a turning around point and it has a derivative there, so the derivative has to be 0. It has to have a horizontal tangent line somewhere in between a and b. All right. So we can visualize that, right? So let's use this theorem to do a little proof. So in this proof, we're going to show that this equation, x to the third plus e to the x equals 0, has exactly one root. Now this may look slightly familiar. Back in chapter 2, we used a theorem called the intermediate value theorem to prove that equations had at least one root. So in this proof, we're going to prove that something has exactly one root. So there's 2 steps. The first step is to do what we did before, use the intermediate value theorem to show that this equation has at least one root. Okay, and then once we show that it has at least one root, we're going to show that it can't have any more. So we're going to use Rolle's theorem to show that this equation can't have more than one root. Okay. Cannot have more than one root. All right. So in step 1, we're going to do what we did back in chapter 2. And in case you forgot, this is what we did. We said, okay, let f of x be the function x to the third plus e to the x. We want to apply the intermediate value theorem. So the intermediate value theorem, that's the one where we found a number where the function was negative We found another number where the function was positive. And because the function is continuous everywhere between those two numbers, it couldn't skip over anything, so it had to cross the x-axis, right? So we're just going to plug in some convenient numbers. So let's try -1. F of -1 is -1 to the third plus e to the -1. Well, that's just -1 plus 1 over e. Now, 1 over e is a little smaller than 1 over 2, so -1 plus 1 over e has to be a negative number. All right, let's plug in 0. So f of 0 is going to be 0 cubed plus e to the 0. Well, that's just 1, and 1 is obviously a positive number. So now we have to say why we know f is a continuous function on the interval between -1 and 0. Well, x to the third is a polynomial. We know that's continuous everywhere. E to the x is continuous everywhere. So f of x is continuous everywhere. So in fact, in particular, it's continuous on the closed interval from -1 to 0. And so by the intermediate value theorem, that theorem tells us, well, it couldn't skip over. It went from negative to positive, so there's some number c in the interval, the open interval, so c is in between -1 and 0, where f of c is equal to 0. So it had to cross the x-axis. All right. So that means the equation we're looking at, x to the third plus e to the x equals 0, has at least one root. Okay, we showed that it crossed the x-axis at least once. In fact, it crossed somewhere in between -1 and 0. So now what we need to do is show that it can't cross the x-axis again. It can't cross the x-axis more than once. So in step 2, let's suppose that the equation actually does have two roots. So suppose x to the third plus e to the x equals 0 has two roots. We want to show that it doesn't. So let's say, okay, suppose it does, and we're going to show that something weird happens. All right? So let's call these two roots a and b. Now, because f of x equals x to the third plus e to the x, we can tell that's a continuous and differentiable function everywhere because it's a polynomial plus an exponential. It's continuous at all real numbers. We can say that it's continuous on the closed interval from a to b. So that means it's continuous at all the numbers in between the two roots, and it's continuous at those two roots, a and b. And also, it's got to be differentiable everywhere in between. So it's differentiable on the open interval from a to b. So now, those are the first two hypotheses of Rolle's theorem. The third hypothesis is that f of a and f of b are the same. So the two roots have the same y-coordinate. Well, they do because they're both roots. So f of a is equal to f of b. Okay, so now we can apply Rolle's theorem. So Rolle's theorem says that there has to be a turning around point somewhere in between a and b. So let's say it's at a point D. So there's some D in the open interval from A to B such that f prime of D is equal to 0 because it turned around there. It has a horizontal tangent line there. All right, so what's the problem? Well, let's look at the derivative of f of x. So if we differentiate x to the third plus e to the x, we get f prime of x is equal to 3x squared plus e to the x. And now 3x squared is always greater than or equal to 0, right? And e to the x is always strictly greater than 0. So 3x squared plus e to the x is a positive number for all x. So there's no way that there's a number d where f prime of d is equal to 0. So that's a contradiction. So this means that our assumption was false, and f cannot have two roots. Those two numbers a and b, those don't exist. So we already proved in step 1 that x to the third plus e to the x equals 0 does have at least one root. And now in step 2, we showed that it can't have two roots. So that means that this equation, x to the third plus e to the x equals 0, has to have exactly one root. All right, so we used the intermediate value theorem from back in chapter 2, something we've used before, and we've used this new theorem called Rolle's theorem to show that an equation has exactly one root. All right, so we'll look at a similar theorem called the mean value theorem and see what that one has to say in the next video. So I'll see you there.